Welcome to lecture 13, in which we're finally going to state and talk about Newton's laws of motion. So there's 3 of those laws, and we've already talked about the third one. So 1, 2, 3. Here's the third one. Now you can find those in your textbook, you can find them anywhere. Let me read them first, then we're going to talk about them. Newton's first law states that an object upon which no force acts moves with a constant velocity. You'll often see it stated in some kind of more roundabout way. For example, an object upon which no force acts will remain at rest if it is at rest, and will continue to move in the same direction at a constant speed, or in a constant manner. So it's kind of said in a more roundabout way, but what it boils down to is an object in which no force acts moves with a constant velocity. Sounds fairly straightforward. Actually, its importance is rather subtle, and I'll talk about that later. The second law is the kind of the one we're going to be actively using the most. And it says this: the acceleration a of an object is given by a is the net force over m, F net over m, where m is the mass of the object and F net is the net force up on it. So we now introduce the concept of mass. And again, I come back to that. And finally, Newton's third law says forces, and that's what we talked about already, forces are interactions. If object A acts a force on object B, then B acts a force of the same type with equal magnitude and opposite direction on object A. So usually it's spelled out, usually see it written without that first line, like forces are interactions, but I think that is really the sort of central message, and why I think in a way it should come at the beginning. And then I also added the phrase of the same type. And why did I do that? Well, if object A acts a force on object B gravitationally, then object B is going to act the force on object A gravitationally. If it's a contact push force, like a normal force, then that's going to go both ways. So it's not just there's a force going the other way, it's also a force of exactly the same type. Which we talked about already, although we're going to do another example or two in a bit. So Newton's third law, right, tells us really what forces are. This is what kind of the key of Newton's third law tells us, although of course in practice when we can apply it, we worry about, B on A on B. Okay. So naively, here's what Newton's first law says. Newton's first law tells us what the objects do when there's no force, so what they kind of naturally want to do. Objects do naturally, like when nothing influences them and there's no interaction with anything, if nothing pushes them around. And then Newton's second law tells us how forces affect the motion of an object. In fact, that is the one that is, includes an equation. A is F over m, where F is the net force. We talked about what that is, the vector sum of all the forces. And usually you'll see it spelled out F equals ma. Of course, that's just rearranging it, and it's totally fine. I wrote it this way to emphasize the sort of cause and effect here. We're saying, look, the acceleration, well, that depends on what are the forces acting, what's the mass. And since the forces have to happen, they cause acceleration. Acceleration doesn't create a force, right? So in a sense, this is the most fundamental way of writing it down, although the sort of typical way you see it spelled out is F equals ma. Alright, so let's just get a little bit more of a feel of what those laws are about. So Newton's first law, right, is there's something missing here. And what's missing is, well, it's a constant velocity, but in what reference frame? That's something we can ask. In fact, and that ultimately relates to the importance of Newton's law. Now, Newton actually said, according to Newton himself, when he wrote this down, he had some notion of absolute space. So you can't see it, you can't taste it, you can't feel it, but it's this underlying geometric structure, the space. There is a meaning to being at rest. There's some hidden absolute space. And to some extent he justified this theologically, philosophically, but even in his time there were challenges to this idea. There's an underlying absolute space, and if you want to read more about that, something really useful I would recommend you read is what's called the Leibniz-Clarke correspondence. This was a exchange of letters between Gottfried Leibniz and Clarke, who was one of sort of Newton's followers, I suppose, intellectual descendants. And Clarke argued for the existence of absolute space, among other things, in those letters. And Leibniz argued that no, there's no such thing. All motion is ultimately relative. Of course, that is putting the correspondence in modern terms. Really interesting to read. You get a really good feel kind of for the time, the thinking, how theology, philosophy, physics, math, they were all interrelated. Not part of our course, but really good to actually read, especially if you care a little bit more about the history and philosophy of physics. Now today we'd say, well, constant velocity relative to what? Because we can pick any reference frame, and we say it's relative to what's called inertial frames. Now actually the logic here is a little bit different when it boils down to it. Really, the first law defines inertial frames, and that is its importance, but I'm going to talk about that in a little extra video, because it gets a bit philosophical and takes a little bit of our main path here. So I'm just going to say see extra video, then I'm going to find a link to that where you found this video too. So we're going to talk about it more. Okay, so one thing I want to say about Newton's first law, though, is that it is not necessarily intuitive. Right? Why is it not intuitive? So on Earth, stuff doesn't seem to be moving with a constant velocity. Right? I give a ball a kick, and it rolls across my front yard. Well, eventually it's going to come to rest. Right? It doesn't keep going with a constant velocity forever. Why is that? Well, of course it is because there are forces acting on it. There's friction with the ground, there's air resistance. So these kind of dissipative forces, as they're called, they're all around us, right? We can't get away from them. And so it is not at all intuitive that no force means constant velocity, because there's just nowhere in our surrounding where we actually find a situation where no forces are acting. We can get fairly close if, say, we slide something across a sheet of ice, right? There's very low friction there, it might slide for a long time. But even there, it will come to rest eventually. So we just can't get away from having forces acting on things, such as friction and air resistance, for the most part. So this really, it's not obvious. And it was kind of a big breakthrough of Newton, so to some extent this idea existed beforehand, such as Descartes had ideas that were similar to Newton's first law, for example. But it's not obvious. And for example, if you go back 2,000 years, Aristotle had the idea that, well, I need a bigger force to get something moving at a higher velocity. Right? Of course, that is wrong. But it is intuitively, it makes sense, because on Earth, if I want to push something big at a high speed, I have to push it really hard just to keep going. Why? Because there's lots of friction, lots of air resistance trying to slow it down. So, not obvious, but hopefully fairly intuitive to understand what it means, at least in the surface. If you actually are looking for scenarios where there are no forces, where Newton's first law directly applied, well, the closest you're going to get is if you go out into space, say, and you look at some object flying through empty space, such as, say, the Voyager 1 and 2 probes, right? They were launched in 1977, and today they've reached the edges of the solar system, and they keep going. Now, they've long run out of fuel for practical purposes, right? So how can they keep going? Well, they can keep going because they don't need fuel to keep going. They need fuel to burn their thrusters if they wanted to have an acceleration. Now, even out in space, you're always going to have some forces acting, namely gravity. So somewhere there's a star nearby, there's a gravitational force. So it's really hard to actually find a real situation when Newton's first law applies, but there are situations that approximate it. Okay. So, in terms of talking a little bit more about Newton's second law, the new concept we meet here, we've talked about the net force, so we haven't really talked about mass yet. So mass, what is this mass thing? So mass, we can characterize it intuitively as maybe something like the amount of stuff. And that's doesn't really tell us very much, but it corresponds to the idea, look, if I have more of something, I have more mass of the thing, right? 100 grams of sugar is different from 200 grams of sugar, and it'll change what your cakes are going to taste like. But physically speaking, let's look at this here. A higher mass, right, means I'm going to divide the net force, whatever it is, by a bigger number, so I'm going to get less acceleration. So more mass, less acceleration. If something is big, I have to push harder to make it accelerate at the same rate. So perhaps a better way to characterize it would be to say it's the resistance to being accelerated. So mass is kind of an inherent property of an object, right? I give you a chunk, give you a piece of rock, and it has a certain mass. It's kind of an inherent property that determines how is this piece of rock going to respond to forces acting on it. Like how much is it going to accelerate if I act on it with a certain force or net force. Turns out mass has a further role to play, namely in determining the strength of gravitational forces, determining the weight. So mass and weight, they're different. I'll talk about that in the next video. Weight is a force, mass is an inherent property. But mass is related to weight, and that's kind of what makes gravity a very special force, in that it relates directly to the weight. Okay, now let's do some examples actually of applying Newton's second law. So just we get a little bit of practice just on the basics. Here's my first example. Imagine I have a box and its mass is 2 kilograms, right? So mass is measured in kilograms, or grams or tons, but kilograms is the standard unit that's going to relate to other, other metric units. So the tension in this rope by which this, like a suitcase or box, is being pulled is 5 newtons. And that's supposed to no other forces acting. There's no other relevant forces I have to worry about. Maybe it's sitting on the floor and there's a support like a normal force from below and it has a weight, but they act vertically in the sideways direction. Just pulling it with 5 newtons. There's nothing opposing it. So what's the acceleration? Well, the acceleration is the net force divided by the mass. Well, the net force here is just the tension. Right, as a vector. The tension is a vector. Just because I don't use a single letter for it, but I write out the word, so what? Right, I can still do math with it. Divided by the mass, because it's the only force. in this particular scenario. So that's going to be equal to 5 newtons divided by 2 kilograms in the direction of the rope. And of course, it comes to 2.5 watt, well, meters per second squared in the direction of the rope. Now, the crucial thing to note here is a newton, right, relates to kilogram and meters per second squared. So let me just make a note of this. Note units. We have F is equal to MA, right? That's Newton's second law, net force, technically. Of course, as a vector. So what are the units? The units here are newtons. The units here are kilograms, and then units here are meters per second squared. Now, what it actually means is that a newton is not kind of a self-standing sort of unit. In 1 newton is literally 1 kilogram meter per second squared. So it's a derived unit. So 1 newton equals 1 kilogram meter per second squared. Derived unit. Right? Meters are fundamental. Somewhere you have this meter stick. Or at least you used to have a single stick, I think in Paris, where it is, behind glass, nobody can reach it. It defines the length of a meter. Now we've changed those definitions at this stage. I'm using certain atomic properties instead, but that's kind of the idea, right? Seconds, kind of a fundamental unit of time. Kilograms, a fundamental unit of mass. A newton, there's no sort of newton somewhere behind glass in Paris. Newton is derived from kilograms and meters and seconds. It's a derived unit. But the calculation is to come back to this. That was hopefully straightforward enough. Let's do another example. Here's our next example. I imagine I have a rocket. The rocket's taking off here, beautifully drawn. The forces that are relevant to this scenario are, of course, the thrusters, and what the rocket does, it pushes hot gas out the bottom, it burns the fuel, pushes hot gas out the bottom, pushing the gas down means the gas pushes the rocket back up by, of course, Newton's third law. If you imagine this is 1,500,000 newtons, I could write that, if I wanted to, as 1,500 kilonewtons, or actually as 1.5 meganewtons. So it's different units, like there are kilometers instead of meters. But newtons, of course, the basic quantity. The mass is 60,000 kilograms. Just going to assume that. The weight is 600,000 newtons. In fact, this is derived from the mass, and we'll talk about how in the next video. Of course, I could write this again if I wanted to as 600 kilonewtons, but, just so I've got fewer zeros around, but I don't really have to. The air drag is 150,000 newtons, at least right at this instant that I'm looking at. Of course, the air drag is going to change as the rocket speeds up or slows down, or as it reaches space, where there's less atmosphere, really no air at all once you get high enough. So we want to find the acceleration. We've got 3 forces acting this time, so you want to find the net force. So net force is all in the vertical direction, so I don't have to worry about components because I know it's all in the vertical direction. So upwards I have 1,500,000 newtons. That's the thrust. And then I want to add those two. I'll add them, but as vectors because they're pointing down to the opposite direction, so I have to subtract them. Minus this 600,000 newtons from the weight, and then also minus the 150,000 newtons from the air drag. What does that make? That leaves me with 750,000 newtons. Okay, so then what's the acceleration? The acceleration is given by the net force divided by the mass. And so I take 750,000 and I'm going to divide it by 60,000. What does that come to? That is going to be 12.5 meters per second squared, which is, it's, I mean, you can visualize it. So all those crazy high numbers, they actually add up to something that's quite reasonable, and you can imagine this sort of acceleration. It's slightly greater than the acceleration due to freefall. And I think that's a fairly realistic value for a rocket taking off, maybe even a little bit higher in reality. Okay, so I hope that makes sense, right? We didn't work out the acceleration for each force, right? Acceleration due to thrust, acceleration due to air drag, acceleration due to weight. It doesn't make any sense. Acceleration is a property of the motion. The rocket moves only in one way, right? So to take all the forces into account, we first find the net force and then use that to find the acceleration. Okay, just 2 examples of Newton's second law. We're going to do a lot more as time goes by. And just to finish off this lecture, I wanted to quickly just lose a few more words about Newton's third law. So some more on Newton's third law. I'm going to abbreviate this as NL3, Newton's law number 3. Just because I'm, of course, awfully lazy. So let's imagine the following scenario. Let's imagine there's some kind of hill, and down here I'm going to park a mine cart. So maybe this is deep in a mine somewhere. Right, so this is my mine cart, the mine cart here. Right, there we go. And then I've got a second mine cart that starts up here. This one's at rest, and it's going to start rolling down through here and hit the other one. Right. So this one comes down, and eventually it's gonna reach this one here. So let's store them again. Now they're down here, and they're going to collide, right? So what happens as they collide? Well, this one is going to crash into this one, right? This one here is crashing into the other one. So it's going to act a force on it, right? So this one acts a force on this one. It's going to be a contact force. So there's a force this way. So this is a contact force due to incoming cart. Note that this card acts a force on this one, so I draw the force on the one that it's acting on. But then, by Newton's third law, right, there's going to be a force the other way on this one. This is, of course, then the contact force due to the stationary card. Right, so it goes both ways. This one can't hit that one without that one also hitting this one. Yes, this one was at fault, right? This one they came racing down the hill, but when they actually collide, the force goes both ways. And so what's the result? Well, this one is going to have an acceleration this way. This one is going to have an acceleration this way, which of course in this case means this one here speeds up to the right, whereas this one here slows down. Why is it slowing down? Because it was initially moving to the right. So it had a velocity to the right, it added a acceleration to the left, there's a change in velocity to the left, so that means it's going to be slowing down. Of course, I hope that makes sense to you. Right, this one would be slowing down, this one would be speeding up from 0 to something, this one from going fast to going a bit slower, or maybe it would even bounce back, depends on the details of the collision, and we'll study collisions a lot more down the line. Okay, so I just want us to be clear about the direction. It's working both ways. It's an application of Newton's third law. Let's look at another example. Very similar. Let's imagine there's a piece of road. Let's imagine there's a sort of big truck coming. Overly drawn truck. Doesn't matter. Here's my truck. Right, truck's coming in. And there's a little car. It's going the other way. Right, truck, I better label those because you can't tell what they are. And they're going in opposite direction. So the truck has a big mass, right? At least compared to the car has a small mass. And now they keep going. Maybe they come in at equal speeds. So now they're going to crash. Right, so here the truck is going to crash into the car. It's not looking very good, is it? So what's going to happen? Well, they're going to act equal and opposite forces on each other. Right? So there'll be a contact force in this direction, pretty much like the mine carts, the contact force in this direction. This is, I'm just going to write F for the force. Right? Same magnitude, opposite direction. Now, what's going to happen? Well, their motion is not going to be equally affected. Right? The force on both of them is the same in magnitude, but the result is not going to be the same. So let's write this down. Same force both ways, but can't spell different. Why is spelling so hard? Different results. Namely, the acceleration of the truck, or the magnitude of the acceleration of the truck, how does it compare to the magnitude of the acceleration of the car? Is it going to be bigger, smaller, or equal? Well, it's going to be smaller. Why? Because the force is the same, but to get the acceleration of the truck, I divide it by the mass of the truck. Whereas the force on the car, well, it's the same as the force on the truck, because those are a Newton third law pair. But the mass of the car is smaller. If the mass of the car is smaller, then when I divide by the mass of the car, this right-hand side is bigger, right? Since m truck is bigger than m car, the mass of the car. Right? So Newton's third law does not say that those two objects have to experience the same acceleration as a result of the force. No, it says the force is equal. What the effect is, well, that is of course determined by Newton's second law, which we used here. Right? So this is by Newton's second law. Okay, so hopefully that makes sense to you. So now, I mean, we've really pretty much established the laws of mechanics. Now the rest is just applying them. Now when you apply Newton's laws, one additional piece you always need to have, an additional sort of knowledge of physics you always need, is you need to know what forces are actually there in a particular situation, right? So if you look back at Newton's laws, it tells us, okay, what happens when there are no forces, what happens when there are forces, essentially when there are interactions. Forces are interactions, they act both ways, but they themselves contain no information about what types of interactions there are out in the world. So that's an additional sort of piece of physics that is to be explored by scientists. It is to be discovered what sort of interactions are there. But really, if you have that knowledge and you understand Newton's laws, then everything else in this course pretty much is just applications, as it were. Okay, so in the next video, we're going to talk about weight and normal forces, sort of honing in on some specific forces to understand them in more detail, but also I'm going to post little additional bonus video in which I explain what Newton's first law actually is about, what its actual role is. And I think that's a greatly underappreciated thing that even the textbooks seem to get wrong or only partially right. Newton's first law is actually a lot more subtle than people think. And I'll explain why there's any question at all about, like, isn't it obvious? No, it's not. It's not obvious what it actually does. I'll explain why, and then I'll explain to you also what its actual meaning is. As I said, you won't find the answer in our textbook. This sounds oddly like a conspiracy. The textbooks will never tell you the answer. No. Its textbook is great. But in the particular case of the role of Newton's first law, it gets it wrong, and so does pretty much every other book I've ever seen on the subject. Alright, I'll see you there.